And as I mentioned that there will be some prize, some surprise at the end of the things, and but before that you have to present. And for the prize, here I requested 4 of my senior colleagues who will evaluate you, and based on that you will get the prize. And surprise I do not know now. So other small thing. Okay, by that time I am little stricter compared to the people you were looked on it. And as I earlier told that, okay, your certificate, okay, that's the one thing I will depend on you, leave it to you. There is a 2 options to get certificate. One is that you come here, one of the senior member will give you certificate. Other option is the certificate will be in the desk, you can go and collect it. And whichever you prefer, this is I leave it to you. I would prefer here, but it will take longer time. So I leave it to you, that part. Okay. And that again I said that I stricter that point that all of you may not get the certificate. But who are not getting, they already know that they are not getting the certificate. Okay. So that's the point. And now I think time is 9:30. Okay, let me first introduce this my senior people. Dr. Sugandha Banerjee, you have seen earlier. Professor Datar, VM Datar. Professor Acharya. And Professor Sugandha Banerjee. Okay, so without taking the much word, okay, other thing, your talk will be 12 plus 3, I just mentioned. And also I requested if you can do 10 plus 5, then they will have a better way to judge you or question and answering. But I leave it to you. But at sharp 15 minutes, whoever is talking, I will stop. Either you or the examiner talk, I will stop there. Okay, so 9:31. So first batch, let's come. You'll come from that set, come you come. So one of your colleagues is there. He's not here. He's there. But no. Experiment 1. This is the height. This.
Okay, myself, Deepak, and today me and our group member, Bhargav and Rasna will present on the lab report. Certainly, but Bhargav is going to be of sick, that's why he not came here. So me and Rasna will present. So this is the overview of our talk. First we will briefly discuss about the horticulture amplifier. Then we will discuss about why we choose and why we prefer charge sensitivity amplifier compared to the voltage sensitivity amplifier. Then we will discuss about the experiment setup and circuit diagram. Then we will discuss that experimental data, and then we will conclude. So, amplifier is an electronic amplifier that converts the electric signal to a strong output signal. So why do we need that amplifier? I mean, because of these two reasons. The first one is impedance matching, and the second one is converting. I mean, as we already know, in HEP, all detector indicated charge one. to converting that charge path to the voltage path, we need to send them to from other external parties. So in we have these three kind of amplifier, current sensitive, and voltage sensitive, and charge sensitive. So first we will discuss about the voltage sensitive amplifier. So here you can see in this B is representing the input signal from any detector or any input signal, and we have represented the output. From here we can take the signal to the some oscilloscope or some other amplifier or some other external circuit. So B I mean for getting a charge for the B means can be equivalent to that, and what is the charge and what is the total capacitor of the input circuit, this is the total can be equal to the state capacitor of the detector, that utility capacitor of the detector. So for the open loop gain is greater than R2 by R1, you can get output like minus R2 by R1 into the input. So we'll get like we have to is proportional to that charge and variable P total. So if P total is changed or capacitor of that detector and the state capacitor is changed, then that gain or output voltage will be proportional to the charge deposited in that amplifier. But if total is not constant for certain type of detector, like for the semiconductor detector, because the operating bias voltage changes when the input capacitor is also changed. So for that case, the gain or output voltage will be like
listen here, other if you do not listen, I will need to go out to control from inside.
so in that for the various detector like we are operating bias voltage changing, then that in their detector capacitor is also vary. For that case, this C total will also vary, and that input or charge may also vary. So for that case, I mean our gain or output voltage will become function of both positive charge also as the capacitor. So for that case, we cannot use this preamplifier for the characteristics of any charge. For that case, we are preferring the charge sensitive preamplifier where our output or gain is to be only dependent upon that what is the deposited charge there. So this is the circuit for charge sensitive preamplifier. So where we are getting any input path from the detector or any other circuit, and here we are taking the output to possible or from other external circuit. So as we know that using for the meter effect, if some capacitor is connected between that non-inverting open input terminal and the output terminal, then the effective capacitor between in the input capacitor become like PF with the feedback capacitor times 1 plus A. So the actual feedback capacitor becomes like P input capacitor plus PF into 1 plus A. So their input pulse will become like charge over total effective capacitance. So for a very large A, we can simplify like this time PF times A will be very high. We can neglect other factors, so we can like C to be like Q over CF times A. So then we can write like B output will be A times Q over CF. So we can say that B output will be minus Q over CF. So we can see that. So B output is only the dependence on the what is the charge deposited, the like charge for Q over CF between the feedback capacitor. So and here we can see one RAT is used to stabilize the condition. So in any the amplifier or amplifier, the gain is defined by the what is the output pulse and what is the input pulse. So here for here we are here we in our case the V output is the voltage pulse and but in our input pulse is like what is the charge voltage. So it is like from this equation can get like it is like 1 over CA. But in principle, it should be a gain should be defined as dimensional quantity. But here it is not dimensional quantity. For this calculation, we use a term like sensitivity, where we define like this. We output by whatever target Q is like we will call like sensitivity will be determined by millivolt by what is the millivolt output response by the what is the charge we will get like picocoulombs. For our experiment,
You have already spent 7 minutes.
so this is our experiment setup. So we have used this printed circuit board with all the components are here. This is the oscilloscope to take our signal from here, and we have used a 9-volt dual polarity power supply and some connecting wire is required to get the signal from power supply to here and output signal to oscilloscope. And we have used like op-amp LF 357 the pin there. So this is the whole circuit diagram for our external setup. Actually, we can generate the input pulse from this power supply and feed it to the here. I will explain the circuit later. So we are getting input pulse there, and from there, and this is the injecting capacitor. We are we are just switching the deficit and changing the capacitor value of injecting capacitor. So it's to the R1 value of like around this is like particular ohm. Then we are changing this deficit and connecting this CM feedback capacitor with this value and the RA of feedback resistance like switching this. And from here we are getting the output part, and here in some setup we will connect this switch current and we will this capacitor will be act like the indicator capacitor. So now we will discuss about the experimental data.
Good morning, everyone. Now we will move to the experimental data. In the experiment, we measure the sensitivity, then the effect of detector capacitance, and the effect of detector capacitance on charge amplifier as well as voltage amplifier. For sensitivity, we can use the charge injecting capacitor value and then the input pulse condition as I will do here. Here, these values are fixed. The input voltage is set to 20 millivolt. In our load, then the feedback capacitor is given a value of 10 picofarad. As you can see here, these are the CL and input voltage is fixed. Then we only vary the injector capacitance value from 27 picofarad to 100 picofarad, and we get the output voltage from the oscilloscope as you can see here, and from there we calculate the Q input and also the sensitivity of the setup. Then in this here we change the V input from 20 to 50 millivolts and keep these values fixed. Then we again calculate the V output from the detector from the oscilloscope, and then we calculate the charge and the sensitivity as in the earlier case. Now we change the input pulse amplitude, but in this case we set the feedback capacitance value to 2.2 picofarad, and we calculate the charge and the sensitivity. As you can see here, when the feedback capacitance was 10 picofarad, the sensitivity was order of 100. But when it is 2.2 picofarad, sensitivity is of the order of 320. Then from there we can conclude that sensitivity is inversely proportional to the feedback capacitance here. Now, we go to the effect. We go to the effect of detector capacitance on charge amplifier. For the first case, we set the input RA and a single value that you can see here. Then we use the feedback capacitor value of 10 picofarad, and without connecting the detector capacitance, we measure the value, and we detector capacitance. We again measure the value, and you can see the change in the capacitance value, output voltage value in here, and also we do the same for the detector capacitance value of 18 picofarad. Now, in the second case, we set the feedback capacitor to 0. In that case, when the feedback capacitor value is 0, the charge sensitive amplifier becomes a voltage sensitive amplifier. Then we get the output voltage, and output voltage difference is obtained to be 120 millivolt. We can see that change in output voltage varies significantly with detector capacitance compared to the charge sensitive amplifier in the second case. We observe another thing from the experiment that the decay of the tail of the output was very proportional to the feedback resistor. It is when the feedback resistor is increased, the decay, the time constant will increase, and thereby the decay tail will also be longer. Now we come to the conclusion. The voltage sensitive amplifiers are more conventional amplifiers, but when the detector capacitance varies, then the sensitivity or gain becomes a function of detector capacitance, and in such cases we use charge sensitive amplifiers instead of voltage sensitive amplifiers, so that the sensitivity becomes independent of the detector capacitance. Although originally charge sensitive amplifiers were designed to use semiconductor detectors, it is probably so superior that it is often used together. There is no need for its specific property. Thank you.
Thank you.
We will relate the oscilloscope, right?
Yes.
So could you comment on the noise level between the two types of Fourier amplifiers? Did you look at the noise?
Two types of amplifiers.
Yeah, two types of amplifiers. You saw both those pulses coming from charge sensitive as well as voltage sensitive pulses you saw. The output pulses. What would be the noise level?
Noise level will be very high, but for voltage sensitivity amplifier, for noise level will be high.
So in this slide, the input voltage is 20 millivolts, right? Will this work if the input voltage was 1 millivolt? I mean, is there a range of input voltages for which these setups work better?
So maybe we know we can just describe some general.
This time,
Because it's a time.
1 minute.
1 minute.
Yeah. So last question.
Now, can you give an example of a detector where the capacitance vary with, let's say, some operating condition like the bias voltage?
In semiconductor detectors.
Which semiconductor? Or all semiconductors?
Okay.
Okay, that's fine.
Thanks. Okay, be ready. This 1 minute count from you. Yeah.
So hello everyone, good morning. I am Avinash Mehdi from Telugu University. This is Sweta Vadia from SIFA Kolkata and Sagar Modak from ISC Bangalore. So today we are going to present our experimental results of pulse shaping and filtering circuits. So this is the basically outline of the talk. This part will give a brief introduction about the pulse shaping and the filtering circuits. Then we will go to the experimental setup, which basically consists of this TRRC circuit, which we will use for the pulse shaping. Then this pole zero cancellation circuit, then secondly circuit, and then we will conclude our findings. Okay. So what is pulse shaping basically? So we have an input signal and we want some some kind of output signal which is of pulse or letting shape. That for that purpose we basically use a pulse shaper. There are different types of pulse shaper actually. In this equipment we are basically using the concept of CRRC pulse shaper. And then basically what happens, pulse shaping actually helps in filtering different unwanted signals of various frequencies that we can do. And then we also that can be also based on the signal characteristics and goals. Then for the importance of the pulse shaping in particle physics, it basically helps us improving the noise as well as the optimizing the signal to noise ratio. Then it also helps reducing the effects of pileup. So basically, if two events from before going to the stable state, if another event comes, then this basically cause the pileup, and that can be reduced using the pulse shaper. And also for different DFT components, the different kind of signals which can be done by using a pulse shaper. Okay. So these are the uses basically of pulse shaper in nuclear physics as well as a particle physics experiment. So it basically enhances the sensitivity of the low level radiation sources. Also, it helps in detecting rare events which has no counts also, and helps in improving discriminating of different types of radiation. For particle physics experiment, it basically improves measurement of the particle properties. Then energy resolution as well as the data acquisition rates can be improved by using a pulse shaper. Okay, so coming to the experimental setup, so we were having like two boards, PCB board, which is board A and board B. For board A, we use basically for CRRC shaping, then pole zero cancellation, and second one is the Gauss semi-Gaussian shaping. So I will explain the working mechanism and the results of the CRRC shaping. Others will be explained by my colleagues. Then here what happens, like a board we actually mark it as different color. As you can see, for like this magenta one, it basically shows the power supply here and here in the board. Then the other like green and other things, power generator, working the circuit for the CRRC shaper, then pole zero, and then semi-Gaussian shaper circuits are shown accordingly in the boards with these blocks. Okay. Coming to the CRRC circuits, so it basically what happens, there is a two circuits. If we look into this green one, so this you can see this is a 1 nanofarad capacitor, and there are various combination of resistor. Basically, this comprises the CR circuit, which acts as we know high pass filter. So it attenuates the lower frequency signal and allows the higher frequency signal. Then there is a unity gain op amp. Then this output of that op amp is fed into this RC circuit, where this is the different combination of R resistance, and this is the capacitor, which is also 1 nanofarad. So what happens? It basically allows the high frequency signals to go into this low pass filter, and low pass filter basically filters the low frequency signals, and basically we get a good shape pulse at the output. Okay, so these are the input. This is the input we have given, and then this is the output. As you can see, this comes as this, and then again I have to say here that this is a CR differentiator, and then RC indicator will combine. Then we get the output as this. If we move into the mathematical formula, this is the output. this T1 and T2 are the time constant of the differentiating and integrating circuits, which is basically R into C, multiplication of power resistance of the circuit and then the capacitance of the circuit. So this is actually very important to point there to minimize the pile-up events. As I have already seen the pile-up events on these pile-up events, the time constant should be kept short so that the pulse returns to the baseline as quickly as possible before the second pulse comes, so that we can distinguish both the pulses if they come at a very short period of time. Okay, so this is the results of our analysis. So basically what happens, we give an input of 5 volts and we measure the output. Then the lifetime, like how much time is it to get to the peak, then how much time to need it get to the base of the thing, and then this is the values of the time constant of the CR and RC circuits. So these are the outputs we got from these circuits, CR RC circuits. Now I request Sagar to explain this whole zero thing. So to explain the whole. So to explain why pole zero cancellation is required, we need to understand what is pole and what is zero here. So the pole is basically when we get an infinite magnitude in the pulse, that is called a pole, and zero will basically when the input pulse touches the baseline, to the signal becomes zero, it is called the zero. So pole is called we use the pole cancellation circuit to basically minimize the noise and overshoot under. So that is what I was told there. So this is the basically the pole zero understood. It is when the pole zero is not there, but after applying this RPZ value, you can see the undershoot has gone and the output is like this. So we need to change the value of RPZ here as the capacitance value is fixed to have our pole zero cancellation. So what we do is that in this circuit, as you can see, that there is a capacitance which is fixed, but we have a resistor box like so we change the resistor box here, and there is also a resistor box there. So if you go to the findings of our results, yes, here you can see there is a CR resistance that is there, and there is a RZ required for this thing. So we change the value of RZ and to minimize the undershoot. So this is the pulse before the pole zero cancellation. You can see there is some undershoot here, but in the after pole zero cancellation, it has gone. These are our experimental findings, and yes, now she will.
Hello. Yeah, so this is a semi-Gaussian shaper circuit, which is also one kind of the pulse shaper circuit. So here you can see the one is the green box is differentiator or high pass filter, the CR, and after the CR we have 4 stages of the. After the CR we have 4 stages of RC state 4 RC stages, which are basically the low pass filters. And finally, we see the output. So here you can see the outputs of the semi-Gaussian shaper circuit. So the first plot, as you see here, is the output of the first CR stage after the differentiator stage, and this plot here is after passing the first RC stage, and as you see, the pulse is getting more Gaussian-like. And here, this is finally the output of the fourth RC state, and now we have a Gaussian looking like pulse. So this kind of shaper circuits are designed to have a signal shape which are similar to a Gaussian pulse. And as I said, these are implemented using combination of the CR circuit and a series of RC stages. And here is a mathematical expression of the output voltage. Whose time and the time constant of the signal is for this kind of circuit is n tau. Yeah. So this is the findings. So on the first one, you can see the pulse voltage, And here on the last two columns, you can see the left half with maximas and the right half with maximas for after each RC stages. And as you see, the distribution gets more closer to the Gaussian pulse as we go on increasing the RC stage. Yeah. So here we have discussed two pulse shaping and filtering circuits, and this can be used to eliminate the errors and improve the accuracy of the measurement. And as the technology advances, this kind of circuits will become more important and will be widely used in many other applications. So thank you for your attention.
Are the requirements of pile-up and good energy resolution, they go along well together, or are they mutually at logarithms? And the second question, okay, maybe you can, maybe you answer the first.
Pile-up is basically going to be when some very closer time. So I think it will help in resolving the load into the pile zones and then I'm not sure, but I like
No, whatever. Okay, maybe. The second question is which kind of would you use the same RCs for all detectors, or that wouldn't matter what detector you use? Let's say a scintillator versus let's say slow proportional counter, or maybe a large semiconductor detector, germanium.
That will depend upon the output energy of the detector. I think the values of the RCs, which we said, because the CR or RC, if I say about the say high.
So typically, okay, what is the time constant that you got? Of course, maybe you didn't do this, but for germanium detectors, large size, what type of time constants are involved? You know? No.
Okay, go back to your last slide. So the first bullet says that you discussed between pulse shaping and filtering methods. So what is the difference between the two? What is pulse shaping and what is filtering?
Actually, both are being done at the same time here. This high pass, as you saw, the RC and CR and RC circuit, those are basically filtering some frequency ranges. So the CR circuit is filtering the lower frequencies, and the low pass or the RC circuit is filtering the higher frequencies. So both together act as a band pass filter. So there is a filter there. And finally, as we saw, the pulse shapes are changing after going through the entire CRMC stage. So there comes.
So this does filtering also mean pulse shaping?
Filtering helps us to have some different shapes.
Yeah.
Hi everyone, we're group 19 and we're going to talk about the times of voltage compared to and the window comparison. So the talk will be split into three parts. First, we'll talk about the time to voltage conversion, and then we'll talk about the comparator measuring hysteresis, and finally we'll talk about the window comparison. So what is time to voltage conversion? It uses the measurement of the time interval between two electronic signals, and it's useful for determining the angle of incidence of an inertia generated by higher energy cosmic rays, and it's used in accelerator experiments. And it's also the first stage in the time to digital converter.
So how do we measure it? So a capacitor is charged by a constant current source, and the total charge is delivered to the capacitor, and is then an analog representation of the time signal. So as you can see on the blue line is our pulse, and then the yellow line is our capacitor voltage. An analog to digital converter is performed back on the voltage by the capacitor, and the charge is removed at a constant rate. So this is the circuit. So we have two NOT gates to induce a time delayed circuit, followed by a deep block. We have some transistors and then a capacitor which is charged, and then in the red is the constant current source. So when there's no charge, Q is low in the deep block. So Q2 is on in the transistor, and then Q1 in the transistor is drained by Q2 to the ground. When the pulse is applied, so Q bar is low in the deep block, Q3 is on, and therefore Q1 charges the capacitor C1. So the Q output of the flip-flop goes again low when the input pulse ends. So essentially the capacitor is charged by a constant current supplied by Q1 for the duration of the inputs. So using the relation that the voltage over the capacitor is proportional to the time that it's charged, we're able to calculate the constant current through the capacitor. So VCCE is the supply voltage to the emitter. V acts as the emitter to the base forward bias drop. The reference is set to 8 volts, and the emitter resistance is RE. So this is the output of the scope. The blue line is the input pulse, and then the yellow line is the voltage over the capacitor. And as you can see, there's saturation where, because the capacitor has a maximum capacitance, it's not able to accept any more charge. So that's why we have this setting. So these are the results. So we changed the pulse width, the input pulse width for the capacitor, and we measured the output voltage over the capacitor. As you can see, that there's the plateau due to saturation, and it's very different to the calculated expected voltage.
Hello everyone. So I'll be just discussing about the comparator circuit ability. So comparator circuit is basically the circuit which is used for comparing between two analog signals or an analog with a reference voltage or a signal. So this is a simple comparator circuit where using the potential divider circuit we set a reference voltage, and in the non-inverting input we give the signal. So in this case, what happens is that when we input signal voltage is greater than the reference, the output of the op-amp reaches the positive saturation level. And in the other case, where the V input is less than the V reference, we get the negative saturation level. That can be seen in the slide. But there is some issue associated with the comparator circuit is when the input signal has some noise. So, this is the input signal. Along the input signal, we have some noise. And if you have just one reference voltage, then the output of the op-amp would be this. And this is not something that we want. Okay, so it can be rectified using using a hysteresis effect, where the comparator circuit working can be improved. So this can be done by implementing a hysteresis voltage range to reduce its sensitivity to noise. So this is a simple comparator circuit with hysteresis, where we basically give a positive feedback to the non-inverting input of it. And this is the hysteresis band that is produced or generated because of the presence of these two resistances. These two resistances basically set an upper limit and a lower limit on the voltage to eliminate the unwanted transition by that operate using noise. So this is basically the hysteresis band that we play. And just for a comparison, so if this is the analog input signal, and then this will be the output of a simple comparator without hysteresis, and this the bottom one would be the output with the hysteresis. So this is a circuit diagram. So the hysteresis band basically depends on the chosen values of RA and RB, where this is RB and this is the set of RA values that we have tested. And the upper limit of the reference voltage can be obtained using this formula, and the lower limit can be obtained this. and the hysteresis band is defined by the like subtraction of the lower limit from the upper limit. So this is the oscilloscope output, where on the x-axis we have the V input and on the y we observe the out. So as I have already mentioned that the hysteresis band depends on the configuration of the resistances of RA and RB. So basically we have like kept RA, RB fixed and then varied RA and vice versa. And then here we have plotted with RA and the hysteresis voltage range. So by changing the or by like adjusting the value of the resistance, we can actually define what will be the hysteresis band size. So that's all from me. I should be discussing about the window comparator.
Good morning, everyone. So our third part was studying about window comparator. Window comparator is used for collecting signals only within specified range or window of voltages. So in window comparator, we logically combine two op-amps, one inverting comparator and second non-inverting comparator, and it employs the two comparators to detect the over voltage and under voltage condition. So here is the circuit diagram for the window comparator. So first we have the non-inverting op-amp, and then this is inverting op-amp. So the input is feeding into the positive of the non-inverting, and the here we are feeding the input into the inverting, the negative terminal. And the reference voltage is given by this resistor divider. We have 3R is equal to 10 k. So we have two voltages, threshold voltages, upper level and lower level. So when the upper level voltage is when V input is less than upper level voltage, then V is equal to low. And when V input is greater than the lower level, then V out is low. We need V out is pretty low to light up this LED, because if V out is low, these two diodes will be reverse biased, and the current will from this 9 volt will glow this LED. If either one of them is high, then this diode will be over biased and the current will be drained. This transistor is saturated and the current will be drained from here. So we need both of them to be low at the same time, and this can be achieved only in this input V input between lower level and upper level. So this is how the window comparator works, and this is our observation in this experiment. So first we calculated the voltages of the upper threshold and lower threshold by a simple voltage divider. For the lower voltage, we have this voltage of this two resistors, and for lower we have this only one resistor. So here this is like 20k or 30k into 9 voltage, that is 4, and lower is 10k by 30k, that is 3 volts. So we measure the expected voltages in upper level and lower level by helping multimeter around the resistor, and this was the resistor value. And then with the help of potentiometer, we increase the V input and see the output to the LED. And when the LED start glowing, we notice the lower value. And when the LED start stop glowing, we notice the upper level of the voltage. That's how we got the window of the window comparator. So I am coming to the conclusion slide. So in this experiment, we learned about TVC and comparator circuits. Both circuits are very useful for analyzing analog signals, and they help in the high energy stack system. So these circuits are basically the building block for the analog to digital converters. So voltage converter comparator is essentially the 1-bit analog to digital converter, as the input signal is analog to the output VSD. So thank you for listening.
Can you go to slide number 8?
Yeah. So in this, the output voltage, why does it saturate?
Because it's reached maximum, so it has some maximum capacitance, when they can only accept so much charge, so that's why the voltage capacitance is not able to accept it.
Slide 10. Okay, so you were talking about hysteresis here, but what exactly is hysteresis?
So it is not directly so here, as you can see, say if this is the upper limit, and if the signal after this goes below, then we expect the output to go low. But in this comparator with hysteresis, that is not happening. It will go low only when it
No, that
is
is
below. So there is a lagging that is happening. So it, what we can say, like analogous to what we see in like mechanism.
Okay, so you know what history is.
Yes.
What is the minimum time that it would be possible to measure using the time to voltage converter that you built or that you use?
So the lowest one we went down to is 230 nanoseconds.
According to this, it's what, about 100, 200 nanoseconds, but is that the limit or can you go lower? Also, another thing I noticed in all your graphs, I mean, you had, smooth lines drawn. You must have made a finite number, as you have in this case, finite number of measurements. Right?
Yes.
They're actually data points.
Yes.
It might have been a better idea to plot those data points with the error. I agree that maybe the error is too small, it's within the size of the, but it's still a good idea to plot the points.
Oh, okay, thank you.
Good morning, everyone. So, we will be presenting FPGAs field programmable gate array. So, you all must have seen different kinds of boards and all, like laptops and PCs and mobile phones and all. But all these boards are actually designed for very specific purposes. So, these can be categorized into CPUs, FPGAs, and ASICs. CPU is the most common thing that you will all have must have encountered. So for example, in our laptops, Intel's i3, i5, i7, or Silicon M1 and M3 i3 processors, all these are central processing units. So they will, they can, for example, our electronic circuitry that executes instructions such as a computer program, for example, C++, Python, or any program. These are very versatile devices because they can do a lot of different variety of tasks. On the other end of the spectrum are ASICs, which are not so versatile because they are designed for a very specific logic also. So, for example, if you have some logic running on an ASIC, you can't actually modify that and run something else on that. You have to discard that and make a new one. So that is like the limitations of ASICs also. In the middle, there are FPGAs, which are, as the name says, programmable gate arrays. So you will have an array of gates, which you can actually reprogram again and again if your requirements are changing. That makes them a little less versatile than CPUs, but they are versatile than ASICs and all. So these FPGAs are actually matrix of configurable logic blocks that are connected by programmable interconnects. Because CPUs have to perform a wide variety of tasks and all, they actually consume a lot of power. And ASICs have to do like only one task, so very power efficient. And FPGAs are lying in the middle. And because CPUs has to again do a variety of tasks and have to communicate with various components, they are actually slow. And ASICs, again for the same reason, only a single task are very fast. And FPGAs lies in the middle. Okay, so what actually are FPGAs? Let us go into a little more detail. These were these programmable logic arrays were actually the first programmable chips.
So they consisted of structures of AND and OR gates, AND and OR gates. So the connections of these AND and OR gates were actually like you can change the connections and all. So these connections, for example, if you turn off any connections and keep only a few of them on, then this kind of structure can arise in the FPGA. So in this case, you are actually changing the hardware of the FPGA on a hardware levels. You are switching on and off various connections. This is same like switching on and off a bulb or tube light or something. So that will actually change the hardware, and that's why you can also reprogram it. This reprogramming is not in this case running some different program like in the case of CPU, but actually changing on a hardware level the structure of the FPGA. So these PLDs and are actually a collection of large number of these kind of blocks. And the actual FPGAs that we use today are actually even more complicated. So these will be these will contain much larger number of smaller individual blocks, and will have a large number of interconnection structures. So these connecting lines which can turn on and off. So these is what the internal open FPGA looks like. Now, Floro will go into more details of FPGAs. Thank you.
So here is a specific basic FPGA architecture. So this is the board that we use during our experiments. So in the middle we have the FPGA with the internal blocks of logic gate, the input output block, and the memory. It's mainly used like even they say for the A5 system, where the response time is really crucial because the FPGA are quite fast. But also when the hardware is likely to change. And of course, the FPGA can execute several operations in parallel since everything works in function of the clock. So I will explain a bit the logic block. So all logic block is the heart of the FPGA. It always contain a local table of the flip-flop, multiplexer, and some gate, and of course the output. This block will create a physical network, and the controller can perform this to realize a specific computing task. And also, of course, we can add to all this block many other elements like the CPU, memory controller, USB, and so the design for the FPGA is basically the function of the FPGA will work. So the hardware we will, thanks to the VHDL very low, we will describe the functionality that we want to use, and we will translate it in a language. And hardware language. After writing our code, we will compile, and this will give us the binary file that we will load inside the FPGA to realize the functionality we want. So a bit of a comparison. So FPGA we will write code that will describe the physical structure. And compared to the other programmation language of code, the programmer will write code that will control the structure and explain how it will operate. And I will give a small example. So this is how it looks like HDL or HDL code. So first we can use some library. Then is the declaration of all the input and output that we need, and then the architecture to map the entry and create the function today. After writing this code, we have to compile the compilation in FPGA in function of different functionality we want to implement in the FPGA can be very, very long. So tools like simulation can be very useful to see our functionality working properly like we would like. So we have the possibility to simulate out our code before compiling. So in this example, I just simulate the use part of my code. So just engage. So we will see on the first line the A colon, so 0, 0, 1, 1. And when the output will be equal to 1, it will to input A, B will equal to 1. So thanks to this simulation, I know that my overall VHDL code is working well, so I can implement it and send it to my feature. So now we will talk about use case.
Okay, so while we have used FPGA, actually, we not only use FPGA in the FPGA lab, but in the IO simulator, we have used the digitizer, and in the digitizer, there is a FPGA board, and in the Cherenkov detectors, there are 16 PMPs, and to read out the PMPs, we have used the digitizer board. So in analog approach, so detector signal coming to charge sensitivity amplifier, and from there stepping amplifier just save the signal to semi-Gaussian, which carries the energy information, and from the ADC we get the energy information to the PC, and this first signal carries the timing information and the position information. So this whole thing from the setting amplifier to computer, this channel to computer, this things does in FPGA module. This thing does in digitizer, and digitizer runs on the FPGA board. So these are the, if we connect this signal to oscilloscope, we get these types of signal from the detector. We get this type of signal, and from preamplifier, and this signal. So this is the digitizer where the pulse processing unit. From pulse processing unit, we get the energy information and the all things. So this is more details. So FPGA, yes, okay. So FPGA board in hardware system, for the each of the detector specified detector, we have to use the detector in every electronic module. But in digitizer case, we have used the single hardware system, and we change the firmware to for our familiar use of my detectors. And for energy resolution, for the 14-bit ADC gives a 16K energy resolution, 16K channels, and let's say for sodium iodide scintillator detector, 1K channel is sufficient for our energy resolution, and for the HPG detector, we need at least 8K channels for the energy resolution. So here there is decimeter, and this is time and trigger filter, and this trapezoidal filter gives the energy information in digitizer form. So this decimeter, what does the decimeter do? Actually, if our signal is too slow, then the pulse processing time is not matched with the signal processing. So we have to scale down the pulse process. So this thing does the decimeter do. And when signal comes, what we do in shaping amplifier, that we save the signal from the PM, and in digitized form we save by the trapezoidal filter, and the height of the trapezoidal filter gives the energy information. So in trapezoidal and in the trigger time trigger, the time trigger
time is over.
from the PDF.
Your time is over. Okay. So question?
And
No, your time is over.
okay.
I didn't get what question did you describe only how FPGA works. But what exactly have you done in FPGA program?
Yes, we have a small program, but we didn't know actually, but
For the most of the time, until we went into understanding the actual architecture and all, we also were given a small program to make a LED blink and change the frequency of that. So,
Yeah, why it will be faster than normal CPU?
yeah, because CPU has actually to do a lot of tasks and all.
No, if you make a CPU only having one task.
Yeah, the feature will work on every rising front of the block. All the tasks will go at the same point and same moment. So this is why FPGA is quicker on CPU. So we can do all the same tasks in parallel at the same moment.
So parallelization is the thing. So if you can make a parallelized program, you can have the same speed.
Yeah.
Okay.
You said for the FPGA, you do the simulation before writing, checking the code like that. After putting the code in the FPGA, how does one check whether there is any mistake in that code or not? Whatever one has put in.
Yeah, we can have some debugging tools or
Good morning, all. Today we are going to present our experiment, which was characterization of raised plate chamber. Myself, Shubham Datta, and Nikhil Ranjan Das, and we are group 11. So raised plate chambers, they are basically gaseous detectors, which are based of spark chamber. And so some of the main features of RPC are they have very good time resolution of the order of few nanoseconds, and a good position resolution also of the order of few millimeters. And another very good feature of RPC is that they can easily be scaled to large size detectors at very minimal cost. And also they have very good performance stability over time. So because of these properties, we can, and because of their fast performance, we can use RPC for triggering purposes, or as counters where maybe there may be high particle flux and we need to count the particles, or as tracker also. So two examples that are given here. One is the cosmic neon tracker, where RPC is used for the cosmic neon tracker in the mini ICFA experiment, and also as neon tracker, neon trigger in the CMS experiment. So this is the basic construction of the RPC. So we have two high resistive electrodes, glass electrode, which is with basically glass plate, and then there is a conductive coating over it, which is basically spread uniformly over the glass plate, through which we apply the plus HV, the high voltage, and the negative high voltage. And then there is an insulating layer, which is basically this mylar layer, which separates the high voltage from the readout strips. The readout strips are basically the ones from which we take the signal. The readout strips are kept both above and below in two orthogonal orientations. So this helps us to get the position of the interaction also. So from this, so these are the readout strips are basically copper strips, and gas is and in between the two electrodes there is a gap through which gas is passed. And this is the gas meter that is used in the RPC that we did, which is freon, isobutane, and sulfur hexafluoride. Freon is the main gas through which the ionization takes place. Isobutane is the photon quencher, and sulfur hexafluoride is the electron quencher. So here I show the basic working principle. So when a charged particles goes to the gas, there is primary ionization through which primary electrons are created, and since there is a very high field, we apply of the order of 10 kilovolts, the potential difference between the two electrodes. So at this high electric field, these primary electrons gain enough energy that they create secondary electrons by elastic and inelastic collisions with the molecules of the gas within the gas gap, and this causes amplification of the signal, which we can call as gas amplification. And as these ions drift towards the opposite electrodes, mainly it's mainly the electrons that has a higher drift velocity, because of which we get signals on the pickup switches, and this RTC is operated in the avalanche mode basically. So for the next one, I will hand over to Neil.
Hello. This is the RTC equivalent circuit. You can see the Zener diode being connected in a reverse bias condition here, with supplying of plus minus B volt across some resistor of the plate, and across the Zener diode in parallel we have a resistor known as R spacer. In case of low voltage, we have resistance across the gap of that means the resistance of the Zener diode to be infinite, and the small change of voltage with respect to current appears across the resistance of the spacer. So in this case, we have no multiplication. At high voltage, we have resistance gap which is equal to 0. The change of voltage with respect to current is equal to the resistance of this plate, and we know that there is high multiplication of the gas and free electrons in the gas increases. This is a typical plot of the BI characteristics graph, where you see the slope of this. This is the Zener breakdown voltage of the Zener diode, and the slope of this voltage gives you the R spacer, and this as we increase the high voltage, the slope of this curve gives you the resistance across the plate. This is the experimental setup where P1, P2, P3, P4 are the scintillator panels, classic scintillators coupled to SIPM, connected to high voltage source of bias voltage of 54 volt. And this is the RTC detector, which is placed between the scintillator, supplied to a voltage separately, and then connected to a voltage gain amplifier, and the output of the amplifier is taken directly to the discriminator. And the outputs of these panels are connected to some kind of pre-amplifiers and then to the discriminators, and the output of these modules are taken to the 4-input AND gate, and the output of these AND gate are fed to the scaler. Similarly, these connections are also fed to the scaler. The main objectives of our experimental setup is to calculate surface resistivity, leakage, dark current, noise rate, and muon detection efficiency. The surface resistivity is measured with the help of a copper zinc placed across all the points across the resistive plate. The leakage is performed to see any leakage. Of the gas inside the electrodes. In the dark current, the noise rate is measured so as to get the optimum high operating voltage. And the muon detection is done with the help of these scintillator panels, which are fed to the scaler. Now I hand over to you for the rest of the slides.
As Nikhil already said, to start with the
keep it in pocket.
As Nikhil already said, to start the experiment, we must ensure that the resistance of the plate must be uniform, and so that we get the uniform electric field between the two plates, and also to ensure that there is no drift of the induced charge due to the difference of the charge, and we measure the resistance of the defined position, and this is the distribution of the charge, and we see that the resistance is quite uniform. Then, since the RTC is sensitive to the pressure, so it must be ensured that there is no leakage in the chamber. So we measure the study the leakage rate by Arduino based setup and Arduino based setup, and this takes 8 hours of time because 8 hours of time, and so that for shortage of time we artificially created a leakage, and we studied the pressure how the pressure fall with the time, and we see with the time the pressure decreases. Now the setup is ready for the experiment, and we first study the current, how the current is changes with the voltage. This current is arises due to the spacer that we do between the two plates, and we, since we do not reach the breakdown voltage, so we get the linear relationship. Please note that this voltage is the twice the voltage, because the same magnitude of the negative voltage is applied on the negative terminal. And with this flow, we can determine the resistance of the spacer. Now then we study the count rate of a single step and with increasing the voltage, and we see that as we increase the voltage, the small deposit of the signal of muon signal can possible to give the signal. So we as we increase the voltage, we see the rise of the count rate. Now, as Nikhil said, the efficiency is defined as the 5-fold count by 4-fold count, and as we increase the voltage, the efficiency is increases, and we choose the voltage at which point where the saturation just started. And this saturation voltage is twice of 495 volt. Now, in conclusion, we see that the surface resistance is uniform out the surface, quite uniform, and we see that since we do not reach the breakdown voltage, so we keep the linear relationship. And we see the single count non-linear response of the single count. And we see and we set the breakdown voltage at 9.9 kiloelectron volt. And thank you for your attention.
What is the purpose of this resistive layer? Why cannot it be just a conductor?
Which resistive layer? I mean, when you are giving to the voltage to the electrodes.
Yeah, where you're applying voltage.
So basically, if we use a conductor, so it basically shield any charge, any induced charge that is being produced within the gas gap. So I will not get any reading in my strips that is above the high voltage electrode. So that's why you are using a raised material for that.
The charge is spread in the metal.
Charge is spread out.
Yeah.
The other thing is you mentioned the time resolution, which is of the order of a few nanoseconds. So is that without any, is that what you get, or is it that you get something better than that?
Actually, there are RPCs that are better performing than that. I think I saw there are these multi-gap RPCs that have, I think, 200 or picoseconds of time resolution. So yeah, I mean, this is a single gap RPC. So in single gap RPC, this is the time resolution that we are taking. But more specialized RPC.
What is the cause of that? I mean, a few nanoseconds versus, let's say, about a nanosecond.
So basically, what I can think of is if the gap is small, so the electron, the drift happens quite fast because the gap is small, and because of which the signal promptly we get it on the surface. I mean, there is no much time lag because the plates are very small in gap. So in multi-layer also, what we are trying to do is we are trying to reduce the gap, but also of course keeping in mind that we also need to give enough trouble to the electron so that it is able to have a good amount of velocity so that more amplification takes place.
And also it operates in spark avalanche mode, so it quite fast reach the signal on the.
Why do we use it in the only the neon chamber?
Okay, so in neon chamber, basically we need to cover a larger area because neon chamber is at the end of the CMS detector. For that we need cost effective detectors. So RPC is the option. I mean, it's cost effective and we do not need very good position resolution at that point also. So RPCs are a good option for that.
It's the noise rate you mentioned, and what is it you do?
Noise.
And we see that the for high voltage, the noise rate is increased. So for small deposition of the neon signal, it possible to generate the signal. So the small energy deposition is also give the count. So the
I'm not talking about the neon deposition. It is the noise rate we are talking.
yes, this is the noise. This is not noise. This is the count for signal stream.
So why it is increasing?
So the
What is it you, what you are getting? What is it?
So there may be some. So we are at room temperature basically. So there may be some thermal electrons that are being created within the gas gap. So at high voltage, the field is high enough that even those small thermal electrons are also getting amplified and is giving a discharge. So that's why the noise rate increases as you're increasing the field.
How close it can be these two plates? What is the minimum distance?
So that-
and what happens if you increase the
Yeah, just a very fast.
So the night, so.
Well, it's one. So that depends on the dielectric breakdown of the gas that is being used. So I think
if we increase the distance, then we increase need more voltage to give the more voltage required to give the electricity.
the signal will be small if the gap is increased basically.
So, we desire higher efficiency, right? But higher noise rate also comes in. How do you compensate?
So one way of compensating is that we again the way we did the plastic insulators, plastic scintillators, we do a coincidence type of thing because then if it's a neon signal, let's say, then by coincidence we can have high efficiency also at the same time, and the noise rate will also not come into play.
Okay.
You see how much the noise rate decreased by?
No, we did not do a coincidence measurement with the RBCs. Only with the plastic insulators.
Okay. Thanks. Okay, like previous group, if you can able to finish early, then you are more kind of discussion.
Yes, okay, so we are group 4 and we are going to present the lab about characteristics of plastic scintillator detectors. And we use muons, big-ray muons as our signal. So first I will give you an introduction to what scintillators are, what PMDs are, and then Vejika he's gonna describe the experimental setup. And then last but not least, Amber is gonna show you our results. So, scintillator detectors are one of the most common types of particle detectors within the field of particle physics and nuclear physics. So they can be used for calorimeters, they can be used for triggers for other detectors, which you might have noticed during some of the other labs that you've done during these few weeks. And scintillator is just a material that when it's exposed to some kind of energy, like radiation or heat, it absorbs the energy and then it re-emits the energy as light. So there are two types of scintillators, the organic ones, which we use, the plastic one, and then there are inorganic scintillators. So in our case, we have cosmic ray muons hitting our scintillator material. That then excites the molecules inside our scintillator, and then it de-excites and creates photons. So our photons then go through this light guide into our photovoltaic tube. And this whole setup is then covered in like special papers. So first there's like a layer of white paper that basically reflects the scintillating light back into our scintillating material. And then we have some special black paper that shields it from external light, which would just create noise. So what is a PET? Well, hopefully you all know this by now, but I'm gonna do an overview anyway. So it's an electrical device that converts photons into detectable electrical signals. So we have our photon here from the scintillator, and then it goes into a PET and hits this photocathode, where it will create, well, you'll get an electron due to the photoelectric effect. And then we have an electric voltage through this PET thing, which will accelerate the electron to the first dynamo, where it will create secondary photons. And then these secondary photons will go to the next one and create more photons, and then we do this multiple times. So this was supposed to be a nice animation, but it didn't work. So you just have to imagine that yourself. Now, I will explain the experimental set.
Okay. So I'm going to explain about the experimental setup. So actually, basic idea of the experiment is we have been given a scintillator detector. So the task is to identify the characteristics of the detector. So mainly voltage, operating voltage, and efficiency and noise rates. Okay, this is the schematic diagram we use. So basically, normally we use several modules, discriminator, then logic, called logic unit module, scalar, time to integer converter, and ADC module. So in addition to that, we have used 3 additional scintillator detectors. So which we used to give the trigger pulse to ADC and ADC. Okay, so when there's an incident light neon coming through, going through the detectors, it will produce a signal, and that P1, P2, P3, P4 are the trigger detectors, and that signal will be fed into the discriminator, and then threefold logic unit. This is the logic. Then output of this threefold is fed into the ADC, and ADC as a trigger signals. And our test detector is the P3, then the signal of that detector is fed into the fan-in fan-out module, and the output of that fan-in fan-out module is one output is fed into the discriminator, and then the output of that discriminator is fed into 4-pole AND gate. So in here, in 4-pole AND gate, one input is the output of the 3-pole AND gate. So here the task is to get the AND operation of the trigger signal and the our test signal, data signal, and the output of that signal, that 4-pole is fed into the scale. So scale we used to calculate the number of pulses, and this TDC we used to get the time difference between the bigger pulse and the signal, actual signal, and ADC we used to calculate the charge, measure the charge. And here we use some additional relay lines. So for that we use some coaxial cables. So the idea is to TDC and the ADC, we should provide the trigger signal. So which we taken from that trigger detectors, and after some delay we should provide the test signal, our test signal. Okay. Then scalar module and TDC, ADC modules are in a special plate called CAMAC plate. So this is the one we can communicate with the PC. Okay, so this is our actual experimental setup. Some images of experimental setup. So here, sorry, you can see the 3-4 scintillator detectors, and this is the CAMAC plate with scalar, TDC and ADC modules, and this one is the discriminator, fan-in fan-out module, and 3-4-pole logic module.
And here, these are the wires we coaxial cables we use to produce these grades. And this one is a special circuit which we use to produce the different voltages for the photometer. Okay, so when you consider about data acquisition system, we use an IM and CAMAC based data acquisition setup, and we use C++ based scripts to read and analyze the data in real time, monitoring the data and to get the noise and count rate and efficiencies. Okay, I would like to invite Upper to continue.
So I'll be discussing about the results of the experiment. So mainly we are interested in 5 different characteristics of our detector. I'll be covering all of them, and I'll first demonstrate the procedure, how we did this, and then I'll give you the results. So first we calculated the operating voltage of the detector and efficiency. So what we do is we gradually increase the PMT voltage with a gap of 50 volts, and then we collect the data for 10 minutes. And then we try to find out all the kind of counts we are getting from coincidence units, without coincidence units, and separate. So what do? We try to find out how many counts we are getting, and we try to divide the 3-fold coincidence by 4-fold coincidence to get the efficiency. So as we see here a plot, efficiency was a high voltage. We see that the efficiency is slowly increasing, and then it is a flat. So this is our operating region where we have reached an efficiency of roughly 96%. This operating voltage has a middle point at 1700. So next important result is the noise rates. So noise rates, how do we define our noise? So something which is not coming during coincidence is essentially noise. We should, if a beyond is passing and giving a coincidence not, then there should be a noise signal only at that time, not say other time. So anything comes beyond that is a noise. So we can see that these are the 3 pedals for coincidence. The noise rate is constant because obviously we have not changed the operating voltage there, but we are changing the operating voltage for our test pedal, and we see that this noise rate constantly increases, and this is called a fit over here, and it will be means useful later. Okay, so now I will discuss the time resolution. The time resolution decreases by the increasing of voltage. So we measure the delay between the trigger logic and 4-fold logic. So this is usually Gaussian, and the mean position gives us the delay, and the sigma gives us the resolution. Finally, we have a charge profile. So we collect all the charge that comes from a pulse, and then we convert it to QDC, which is charge to digital converter, and then we plot the most probable value, and you see that this charge is increasing quadratically as well. So we see that the response of our PMT is non-linear. So the conclusion is the operating voltage is between 1650 to 1750 volts. The efficiency is nearly 97%. The timing resolution is 1.2 nanosecond near the operating voltage. The noise is increasing with the voltage. The merit of this kind of detector is that the excellent charge detection efficiency has fast signal response, and can cover large area for relatively small costs. There are some demerits as well, which can be mitigated to some extent. So we have poor energy and position resolution. We have poor detection efficiency for gammas. So the takeaway from this talk is classic scintillators are your go-to if you have just want to count the charge particle like me, and you use them as well. Thank you.
Thank you.
Can you go to slide 2? I think it was showed the photo multiplier tube. Maybe I heard wrong. You said that the larger number of Okay, the other question is, why don't you just use 2 final detectors, coincidence, for
yes.
muons?
Yes, so if you use 2, then your possibility of chance coincidence.
Is it just that, or is it something more fundamental? I mean, more elementary than that.
So
what are the kind of backgrounds that you have in the coincidence backgrounds?
yes, so coincidence we have natural radioactivity outside rates, means cement K40 and then uranium, thorium, these kind of, then there are dark currents also in our detectors, PMPs. So these are usually the noise source in our detectors. So theory is that if we have more of them, then chance coincidence increases.
So what is coverage of this white paper, not for example, the aluminum foil?
Sorry.
Why do cover of the simulators with white paper, not with aluminum foil? That will be
Yes, so this stylus paper give diffuse reflection, not this angle of incidence is not equal to angle of reflection. So in this case, your timing response is better. So it's kind of counterintuitive, but if you have more number of reflections, then your pulse will be slow. But if you have kind of diffuse, then it will be faster.
So, in the same question, did we study this noise rate in 2, 4, 3, 4, 4, 4 coincidences? See how it is?
No.
Because otherwise, why 4, 4 when you have, I mean, we get noise reduction with 3, 4 rows. So, the other question is just so, this slide 5 or 6, go to slide 6. So you have those cables, right? You said they are coaxial or what you said. So what is the meaning of coaxial and why coaxial?
So in coaxial cables, there's a outer shell. Yeah, because and also in coaxial cables that have fixed resistance and fixed resistance. So that's why you then it will not get affected by the noise of that's how it's.
Okay, thank you. Okay, we will take one more before the tea break. Okay, so next one.
Yeah. Hello. We're John Meanwhile, and this is a presentation on the high resolution gamma spectroscopy lab using high purity uranium. This is a quick overview. I'll talk about gamma ray spectroscopy and its effect generally. Dr. will discuss the results, and meanwhile we'll discuss the described applications of high purity uranium beyond what's done here in this lab. Before we start talking about the detectors, we consider 3 separate light match processes. This being called scattering of the electron-electron interaction with electric absorption, which is the big resonance of photon, and then electron and pair reduction. The current of the electron photon pair is induced by a high energy photon. You see there. Here on the right as well, you see the effect of cross sections of each of these interactions with photoelectric dominating the lower energies, pair reduction at higher, and compounding kind of distances everywhere. There are many different materials that we use to detect these processes in gamma ray spectroscopy, two of which being semiconductors and scintillator. In this talk, we'll use high purity uranium or this lab to detect and measure gamma rays from 2 radioactive sources, being 60 cobalt and 152. We'll use the detector to calculate relative characteristics, with the detector being its resolution and efficiency. And as you can see there's the actual crystal you can determine. So just to make a comparison, sorry for all the text, simulated function by the emissions with visible light from the scintillating material by the previously mentioned processes, and purity were added to ensure that the emitted light of the scintillators are visible or detect or within the visible or detectable region of our photon spectrum. And then consequently detected with TNT from other devices. They're generally quite low cost, but have a poor resolution when compared to semiconductors and detectors. Those work in much the same way, but instead of just scintillation light, they work by a reverse bias voltage across the material, producing a region of no free charge or a completion region. So when a charge particle passes through it, it is like whole pairs, and consequently uses the electrical currents. Unlike scintillated detectors, impurities need to be removed to improve the depletion region within a detector. They have a higher cost, but a greater resolution compared to the NI scintillators. Here's a lot of pictures just to get you distracted very quickly. To explain the experimental setup, we have the physical apparatus on the right. I don't know including the uranium crystal, the source within lead shielding, the electronics to connect to it, and a liquid nitrogen container. The The germanium detector is connected to a preamp, which you can see over here, which connects the detector to a trigger on a pulse timer. And it converts the collected charge code by the use of the field effective transistor. And then the output goes to the amplifier and fed to the DAC system or the oscilloscope. See from the plot. So the method of plan for this experiment was to collect data from the emitted gamma rays, if you wrote in 152. We calibrated the detector using the known 152 gamma ray energy levels, that you can see. Well, actually, I've got the cobalt ones here. As you can see, this is our output, normally it's with the ADC. And we can compare it to the expected outputs here, calibrate it. We then determine the energy resolution and relative efficiency of the detector with respect to the energy of the curve. Yeah.
Okay, so as John mentioned briefly before, calibration, we take these known gamma peaks, as written here, deeper energies in a kiloelectron box. So what we do generally, for most part of the experiment, you select each peak and you put a Gaussian over it, take various different parameters of the Gaussian, which we will use now. So the first we used was to calibrate the detector using the 152 open source. Like I said, Gaussian is fitted to each peak, and in this one we took the mean of each peak, where the mean would be the channel number. And then we fitted using this equation here, where E the energy, X is the channel number, A, B, and C are different constants. As you can see here, the quadratic term is actually very small, you can see. This exists because the higher energies, it does take a quadratic shape. Okay, then the second thing we do is the energy resolution. Again, putting a Gaussian across each peak. In this one, we take the full width of maximum from the Gaussian peaks. You divide this by the energy, this would be the resolution. Then we'll fit up this form here, put in the data. Slight shifting white code by A, you can see, but the shape is dominated by these two terms. And then finally, with the photo peak efficiency, again from the spectrum graph, the Gaussian, here we take the area under the photo peak and we divide this by known intensity weights from the data booklet, plus different gamma ray energy that you can see from, let's go back to actually, you can see from this graph here, different gamma ray peaks, again, be more probable than others. So to make it a relative efficiency, you have to divide it by these known intensity weights of each gamma peak. Yeah, and then finally, we've got a split of ours, beta equals A, B over E, and C over E squared, and these are our final parameters. And I'll pass you over to me now.
Hello. So now let's we come to the last part of the presentation. So we have shown the plots. So we have basically measured the three things. So energy calibrations, energy reservations, and the peak photo peak efficiency. So what are they and why is this important? So energy calibrations is basically the relation between the channel number and the energy, and it is important to estimate the energy of the unknown source. And for what is energy calculations, it is the ability of the detector to distinguish between the gamma rays of different energies, and it is important for identifying and characterizing complex gamma ray spectra, which contains the availability of multiple sources. And the last thing, that is the photo peak efficiency, which is actually is the relationship between the detected gamma ray energy and the number of gamma rays that produce a photo peak in the spectrum. So photo peak efficiency is basically needed to correct the loss of gamma rays, the imperfect detection efficiency of the high purity germanium detector. So coming to the last slide. So among the various applications of high purity germaniums, we have included a few of the applications, and it has a wide range of applications in various fields. So we the first applications is in nuclear spectroscopy. So this detector, this high purity germanium detectors are widely used for gamma ray spectroscopy to identify and quantify the radioactive isotopes in samples. And for environmental monitoring, so these detectors can be used to measure and monitor environmental radiations level in soils, water, and etc. And this could help to ensure the public safety. Okay, for the medical imaging, so high purity germanium detectors are used in medical nuclear medicines for imaging and diagnosing various diseases and medical conditions. And for material analysis, it can be used for material analysis, so such as the identifications of unknown materials and the quality controls and forensic investigations. But last but not the least, so in astrophysics, it can be used in detection of gamma rays emitted from the celestial sources, such as the supernovas, pulsars, and the black holes. So, and thus we conclude our talk. We would like to thank the gamma ray spectroscopy team of TIFR and ICFA school organizing members for giving us the opportunity to conduct the experiments. Thank you.
Thank you.
Go back to Tuesday, you showed the dependence of the energy resolution on energy, right?
Yeah.
One can understand the first two terms rather than not the efficiency. What is the origin of the third term?
Yeah, just the different polynomials, just not the shape of the polynomial.
Okay.
Okay.
Go to the next slide. Slide number 10.
Yeah, please tell me.
Yeah. You expect to be this the third term to have a negative value?
C is
You
negative.
expect C to be negative?
The reason we like that is because you expect that the polynomial P64, but just going back down to the KV, we're missing a component of the spectrum that bit with the correct. So that's why it's so wrong.
No, it cannot be the exact answer. It cannot be negative. It should be positive.
Yeah.
It is not.
Yeah, you use the detector with the liquid nitrogen. What happens if you don't use that? If you operate the detector with the low temperature?
I'm assuming the purpose, well, as far as I understood, liquid nitrogen was done to go just the entire setup and you understand thermal noise from electronics or interaction with the material, then which is more noise. I assume it would just reduce the resolution across the entire detector, but I'm not entirely sure that's technical more than anything.
Vertical bars on these points.
So can you read that?
Errors.
Yeah. How did you build?
Okay, so this was for the photo efficiency, so this was calculated. The efficiency was, yeah, the area divided by the photo peak, so there was an error on the known intensities, which was from a data print. And then there was an error on the area that was taken from the Gaussian peak that was fitted over each peak. And they just added in quadrature.
Yeah, the error on the Gaussian peak is a kind. How did you get the reason for the?
It was just from a video program.
Okay, thanks. We will have it in there. What can we touch back? 12 now.
So what are these micromegas? Basically, micromegas are gaseous structures, and they are current plate chambers. As you can see here, we have these two plates here, where the amplification is taking place in this three gap here, separated from the three region by this fine mesh that you can see here. It's a metallic mesh. So this design actually of the detectors allows short read time and fast absorption of positive ions in this metallic mesh here. And this application, this technology is suitable for high rate applications, providing a good time resolution in over nanoseconds and a very good spatial resolution of around 60 micrometer. This is a highlight of the micromega application in experiments. I'm highlighting here the Atlas experiment, where we use the micromegas in the new small wave, which is the first system of the neon spectrometer, which is located actually in the forward region of the Atlas experiment, where we have very high irradiation. So micromegas, they are used here in Atlas to provide a good track for the neon detection
because they have very good special resolution of 60 micrometers. So we have roughly around 2,000 micrometers textures installed in the Atlas cover. And this actually was inserted in the Atlas experiment around 2 years ago. And it is supposed to represent also the high luminosity HC at where the high luminosity around here will have 10 times more luminosity. Moving now to detection principles, so should we want to tell more about this? Okay, so thank you, Austin. I will be talking about this detection construction and this detection principle. So micrometers are parallel plate detectors composed of a very thin metallic micromesh that is placed inside this drift cathode and anode. The gap between this drift cathode and mesh is of the order of millimeter, and the gap between this mesh and this anode is of the order of hundreds of micrometer. The anode is kept at 0 volt. The mesh and the drift cathode is kept at a very negative high voltage, and the mesh voltage is intermediate. Now, due to this small gap, the electric field inside this mesh and this anode is very high, which is of the order of 50 kilovolt per centimeter, whereas in the drift region, the electric field is of the order of 100 volts per centimeter. Now, talking about this mesh structure, our mesh hole is of the order of 45 micrometer, and the pitch is of the order of 63 micrometer. Now, due to this high electric field between this mesh and this anode, the mesh will tend to bend towards this anode, and to prevent that, we have some pillars known as the spacers. They are basically insulating material that keeps the fixed gap between these two, between this mesh and this anode, such that we get the uniform electric field, because we want the gain to be constant. Okay, now due to this, due to the field gradient at the entrance of this mesh hole, we get a funnel-shaped electric field that I will explain later. And due to this funnel-shaped electric field, we get an electron transparency which is pretty close to 1. Now, talking about this working principle, when one radioactive particle falls in the detector, it creates electron and it creates ion. Now, these electrons and ions get drifted to cathode and anodes respectively, and this is known as the charge transport. And when this electron falls into this amplification gap, due to the high electric field, they get accelerated more, and it creates secondary ionization. And this process continues. This is known as the avalanche. And then this movement of electrons induces the charge in the electrodes, and we get the signal. In the right-hand side below figure, the electric field is shown as a function of depth, and we can see the funnel-shaped electric field inside this detector. Now, there is one important property which is known as ion feedback. So, as we know, the ion drift velocity is very less compared to the electron drift velocity, and it leads to a slow pulse state. Now, remember, the signal that we are getting is not due to the charge collection; it is due to the charge movement, and that is why the slow drifting ions give the long tail part. However, micrometers provide intrinsic feedback for this intrinsic ion feedback suppression, and this can be explained by this figure. We can see that these ions are getting absorbed, or it gets near to this mesh, and it takes one electron and it gets neutral. And this neutral argon again can be used as an event can create the electron hole pair. If we look at the pulse, the x-axis is plotted in terms of time, the y-axis is plotted in terms of voltage. You can see that the sharp rise due to this avalanche process, and due to the sharp fall due to the first electron capture in this electrode. However, there is the slow ion tail, that is because of the slow drifting velocity of the ions. Now, that's it from my side, and Neeraj will explain about this detector characterization.
So, though you have seen this figure just a few slides back, but why I put this figure is, there are a couple of factors which are in our control while we are building micrometers. We want our efficiency to be high, we want transparency to be high, we want fields to be uniform, we need good gain, we need good resolutions too. So, how can we get that? So, the control we have is over the fields. What sort of field we apply in our drift region or in our amplification region, and what sort of gas do we use. So we need ionization. So we want
to use the gas which can provide us good ionizations. And apart from that, we don't want any sort of extra charges which sort of replicate our signal to be created. So with that, in order to get a quick signal, we want drift velocity of the ions and the electrons to be high. Also, the Townsend coefficient also should be high. So that, other than that, there are a couple of combinations of the gas which one could use, but how shall we decide which one is the best for us? So there is something called attachment coefficient. We don't want our the electrons which we have created as a result of ionization to be attached back to the argon. So here you could see for the different combination of gas, the minimum attachment coefficient we have in the red is for argon and isobutane. And that is the reason here, at least in the institute, we work with argon and isobutane in this proportion. Now, other things to look for, here you could see if we have even a little amount of O2, there is a different, the attachment coefficient is quite high, it increases. So ideally, we would want our detector to be leak proof so that there is no oxygen going inside it. Now, here for the characterization, we used iron 55 sample and we kept the field in the amplification to be same and field in the different drift region, we varied from 500, 600, 700 and to 1800 around. So there the mesh has a field at 500 and we kept drift also as at a 500, and from where we are getting a signal, we kept it as a ground. So here you could see the electric field in the drift region would be very small, so there won't be there will be diffusion of the electron. So that's why the signal here is quite small. But as you increase the field, you could see there is an improvement in the signal. But again, what happens? It goes down. So the reason is 2 minutes. The reason for this is, as Sudipta explained, the focusing mechanism we have because of the field get decreased because the field from the drift region is also strong. Yeah, so that is the reason it the gain goes down again. Yeah. So here we could see the maximum the drift voltage we should use is at 1200 to achieve the maximum gain. And here, so we are getting two peaks. One is at around 5.9 and another is at 2.9. So we did the fitting and we calculated the efficiency of the resolution, energy resolution, which is coming around 16% for 2.9 peak, and for 5.8 it is coming around 10%. Yeah, so there is a summary. So we prefer micromegas because it is a hard radiation hard. It has a good time resolution, and it is in the Atlas they are used as a vertex detector. That is all from our side. Thank you so much.
You mentioned about high rate capability. Slide number 8. Yeah, you see there's a slow ion tape. So when there is a pileup of pulses come one after another, that gets bigger. No? How do you paint that?
So we sort of only, as I recall, we only look for when it is going down, and then we keep a fixed width, and we select that only as our signal.
Yeah, that's correct. That is if there is only one pulse like that. But if there are many pulses pile up, when the high rate comes,
yeah,
that will be more and more. So the next pulse comes within 250 nanoseconds. The second pulse comes, it will write down that. No?
Okay.
It's slide 10. What is this attachment coefficient? What is the meaning?
So when there is an electron ion pair is created, we don't want electrons against, which is the result of our signal, to get attached with the argument. So because that leads to the decrease in our signal. Yeah,
that is my policy. That we wanted to have minimum as possible. That's why this 90% argon and 10% isolute, and you can see it is very less. That's why we are doing this. Yeah.
What is the cost limit your position resolution?
The position resolution. So here we did not calculate it though, but it is a
Source.
oh source. So we
What limits the position resolution?
Okay, so the diffusion in the gas actually limits the position resolution. If there is a diffusion, it will increase the width. So basically, the electrodes, we are getting the position from the electrodes, position information. When the charge moves, the induced charge in the electrodes also changes, and that width of each electrode limits that, as well as the diffusion coefficient.
Okay, thank you.
Hello.
Yeah.
Okay, thank you. So, hello everyone. Today, the group 26 will present the gamma ray spectroscopy using inorganic scintillators. And yeah, so this is the outline of the talk. So I will start with the motivation and sources of the gamma ray radiation, and then we talk about how they interact with the photons, or how the photons interact with matter, and then the different detectors that are used to detect gamma radiation. And then Samadhan will go over the basic principle of scintillators and the PMTs, and then the experimental setup for the gamma ray spectroscopy. And Dimitri will summarize the results that we have using this experiment. Okay, so this slide 3 shows the highlight the motivation. So gamma ray spectroscopy involves the size measurement of the gamma photon energy, and it can there are multiple applications for this. One is establishing the nuclear energy structure. Second is the identification of radioactive elements, and multiple application in the medical fields as well. Some of the sources that I have highlighted are the radioactive element. Gamma photon is radiated from the excited nucleus when it goes to a ground state or the relaxed nucleus or the less energy state. And then we have the very high energetic gamma rays coming from the astrophysical sources, but we will be focusing on the gamma rays from radioactive source. And how to detect gamma rays? So we need to know how they interact with the matter, and then we need to find a detector that can convert that interaction into a detecting pulse. Okay, so on slide 4, we have the interaction of photons with materials. So there are 3 major processes. I will not go into the main details, but I will just highlight the few important points. One is the photoelectric effect that is very important for this purpose. The cross section for this have a very high Z dependence on the material. Then it also improves, if we use high Z material, it also improves the it also improves the photo peak efficiency. Then other is the complex scattering, which is dominating within the intermediate energy range that you can see on the plot that's showing the cross section versus energy for different processes. And then it also, this gamma rays coming from the complex scattering will suffer multiple scatterings unless or unless it gets absorbed or it escapes the detector. That actually gives the result to the continuum CS background. And then we have the electron positron that also positron annihilation results into single and double peak. So now coming to the different detectors, so there are multiple options. One is the scintillator that we will talk about today.
The gaseous detector we cannot detect directly because it is for the charged particle until unless the photon convert to charged particles via some interaction. And then the solid state detector, in which the pure germanium has better efficiency and better resolution, that I think other group has talked about it already, but I will highlight one point, that it is very costly and not for higher energy gamma detection we need a bigger crystal, and that is really not easy to make. So now I will go over to next slide, and then someone will make it.
Thanks, Alpana, for this comprehensive introduction. So with this, we can move to the experimental methods that we use and discuss. So as you have already mentioned, we use scintillation detectors for detection of gamma rays. Excuse me for some of the repetition as in the previous talk. I just stolen the main slides. Kidding. So I'll just move quickly without much details. So as can be seen, so scintillation is basically can be defined as luminescence which is induced by the ionization radiation when in a transparent dielectric media. So let's say there are two major components in the scintillator detectors. First of all, the scintillator itself, which detects those gamma rays and produces the photons, which are then detected by those photosensors and obviously multiplied for the practical purposes. After that, there are different types of scintillators, can be categorized as organic and inorganic. And the basic difference in these lies in the band structure. What we use is the doped or say extrinsic inorganic scintillator detectors, where we add some impurities called as the activating sites, where we get these bands inside the forbidden band, and we reduce the reabsorption and also the possibility of getting the visible photon for the detection in the photodetector. Okay, so obviously after that we have our photodetector, which converts this electronic signal into the electronic signal, light into the electronic signal. The main key parameter is its quantum efficiency, which can be defined as number of the electrons produced per the photon impinged on the photodetector plate. So this is again the photomultiplier used for the amplification of the light we get after the photocathode. So it consists of a photocathode and a series of diodes. So the basic principle can be seen here is the photocathode, which is influenced by the incoming photon, produces the electron, which are then passed on through a series of diodes, which are at higher voltage, higher potential difference compared to the previous one, and that is provided by this voltage divider resistor circuitry. So the gain can be typically defined by the diode gain and also the number of diodes. Let's say if you have 10 diodes with average gain of 4, will have a roughly gain of 10 to the power 6. That's pretty amazing. And obviously, there are some limitations of it. Obviously, first being its the requirement of higher operating voltage. Also, it is we can see that the charged particles are traveling inside these diodes. So if you have the magnetic field, it will definitely affect the performance. And obviously, it is bulkier. So the recent advancement gives us a better alternative, silicon photomultiplier that we studied in this particular school itself. Okay, so I'll just talk about the experimental setup. So this is roughly the schematic of the setup that we used. So we have our radioisotope. We have used cesium-137, cobalt-60, and the europium source for the gamma ray spectroscopy. We have our photomultiplier tube after the scintillating crystal that we place here. And after that, we get this is the high voltage source, and we have a readout system based on the multi-channel analyzer, it's called as the digitizer, which interfaces to our computer, where we get our signal and fitting and everything can be done in the software program.
So I'll skip this thing with interest of time, and I'll invite Dimitri to show it to you.
So, our experimental results. We used to solve our sticker using two types of crystals, sodium iodide and titanium bromide, using two different electrodes, barium and copper. Here you can see a sticker for titanium bromide crystal. It has advantages in huge outcome signal that leads us to a better energy resolution around 3%. And but disadvantages the huge background because of the technology of one time and huge cost of this crystal. Another top picture you can see backgrounds for titanium crystal without any gamma ray source. Here you can see better degree of titanium alpha decay and gamma ray spectrum. So titanium has background up to 2 milli, so it's affected our results. If you put here gamma ray source, 137, we will see a sharp peak around 660 kilowatt volt, and the resolution here is about 3-4%. Resolution is can be defined with this formula. It's a ratio of full width at the half maximum and energy of our in terms of percents. So sodium iodide it doesn't have any internal reactivity. That's why we don't have any backgrounds without our isotopes. This is a figure for sodium also. Here you can see photoelectricity peak. It's a peak of absorption of our energy of gamma ray. Here is control scattering. This one is the control scattering peak. And on a red picture, you can see compared to our resolutions for two types of crystals, titanium bromide and sodium bromide. So sodium has both outcome signal leads to lowest about 6-7%. So using two types of isotopes, barium, this one, and cobalt, cobalt has two gamma ray peaks. This one, we calculated our stars match and the counts to our energy. To first identify unknown peaks of first source of gamma rays. There will be a picture to another picture. You can see a figure for the source at sodium bromide crystals. And here you can see 6 peaks that we calculate. We immediately can then calculate this energy. And in the right picture, you can see the same picture, but in titanium bromide crystal after subtracting the background of the relativity. Then we use our calculation line, calculated our energy for each peak, and compare it with measurement of this peak using ICFA detector. So you can see a good line, and you can see that the behavior of them are similar to each other. Under around 35 degrees. So in conclusion, with this work, we saw our spectrum in different types of isotopes. Compared the two crystals, sodium iodide and titanium bromide. So the advantages and disadvantages, calculated energy resolution of them, and identified peaks, compound scattering, photoelectricity peaks, and so internal relativity of titanium bromide crystals. Last but the last conclusion is in the final slide. So as can be seen, the instrumentation, especially in the handle physics, that we got the idea is actually a game of compromises and between the signal and background and of course money. And in these 15 days, we got the rules. Thank you.
Did you look at these lanthanum bromide, I mean, the PMT signals on the oscilloscope? Did you find any difference between sodium iodide as well as lanthanum bromide?
So lanthanum, we didn't look at it, we looked at only for the sodium iodide.
You looked at the energy part of it, energy response.
Mhm.
You didn't look at the time response.
No, time is not within.
Also in the linearity with respect to energy, how low down in energy did you go?
So we, I think, 1000 of keV2, so that is the cesium Kurzweil peak.
What about the low energy europium?
Europium, we were able to detect, I think,
That was just to
200.
identify.
I think 200, some.
Because the linearity is also different for these two.
Yeah.
Lanthanum bromide is much more linear. I don't know if you noticed it in there.
Yeah, and as for the higher energy, the linearity also loses. That we didn't go for the higher energy.
So, slide 7. Yeah, so you have these two simulated types, right? Organic and inorganic. So you tried the inorganic ones. So what can you compare with the organic?
Yeah. So organic, for this energy range, we will have less light output. So organic are much faster, but the light output is not that good. So it's a little bit worse resolution in this energy range as compared to inorganic. So we prefer inorganic. So how much worse? So sorry, okay. I just know that how many number of photons that will be coming from the plastic scintillator with the same energy and for the sodium iodide. So sodium iodide it is 30K, but for plastic scintillator, I think it is roughly around 30K per MeV, so it is roughly around 10 to 20 per MeV. But not fully sure about it.
Okay, thanks.
Very good afternoon to you all. So we are group 27. So we are going to present, me and my colleague, Lakshmi and Samar, we are going to present about the basic studies with silicon photomultiplier. So the outline of the presentations, we are going to give some the basic introduction and of SIPM and the working principle, and my colleagues will present on experimental setup, results, and inference. But the silicon photo multiplier. So this is a two-dimensional area shown in this picture that is resistively connected together in parallel. So they are working in the Geiger mode. So they are connected in the reverse biased, working in reverse biased. So the working principle is when the photon is knocked into the region. So when it is depleted region, so they are going to produce. They are going to knock and they are going to produce the electron hole pairs. And because of the bias potential applied in between this region, the electrons are, the charges are going to drift towards this, and this region is very, very thin, and with this potential difference applied here, they will be accelerated towards here, and on the way, they will produce more avalanche, and they will produce the signal here. So this is the variation of the electric field of this inside this device. So the experimental setup, so we will proceed, right?
So here we have the experimental setup for the silicon photomultiplier, and this is the picture of this black box where we have the pulse LED and the silicon photomultiplier. Here we have the arrays of silicon photomultiplier, but we are considering one for this experiment. And it is a 2x2 millimeter dimension and consists of around 1600 microcells. Microcells having the 15 micrometer in each. So we have used this source meter to provide the vascular SIPM, and the LED with the peak wavelength of 465 nanometer is connected to the wave function generator.
and which is which gives a pulse of 415 hertz. Now the SIPM signal is amplified by this trans-impedance amplifier having a gain of 9090 and the data is offered by the parameter. So next I will be discussing on these visuals, which is the IV characteristics of the SIPM. So here we have the two plots overlap. One is when the LED is on and the dark mode, that is the LED is off. So you can see the current increases exponentially as the bias voltage increases. And since the noise rate is too higher, like of the order of 10 to the 6, comparable to the signal frequency, the noise dominates the device current every time. So next we calculate the photoelectron spectrum at different high voltages. So here one of the signal pulse, which is voltage versus time. And if we calculate the charge contained by this pulse, that is simply the integration over this area, which is described here. On the right hand side plot, we can see there are some distribution of the photoelectronic peaks. For example, the peak at 0 is for noise and the peak at 0.3 picocoulomb. This is the charge distribution for one of the photoelectrons, and similarly the peak at 0.6, that is the distribution for 2 photoelectrons. Now, if you want to calculate the gain, then you have to take the difference between these 2 peaks for different photoelectrons, consecutive 2 peaks. And the gain is nothing but a division over this gap between these consecutive photoelectrons over the electronic charge. So next we plot this gain for different bias voltage as mentioned here. So what we observed is the linearity, that is like all the data points are falling in a linear shape, and if we fit it with a straight line, so we could calculate the breakdown voltage and the slope. So basically when the straight line is emitting the 0 on y-axis, that is our breakdown voltage, because this device is made to operate over the breakdown voltage. That's why when the gain is 0, that is the point. That is our breakdown voltage. Next, the noise part will be discussed by.
The noise in the SIPM signal occurs because of the thermal electrons, and also carrier can be trapped during the avalanche and then release the triggering another avalanche. And also it may be because of the crosstalk. In the crosstalk, some of the discharged photons on the avalanche can be absorbed in the adjacent cell and triggering the new discharge. So these avalanches also can create the signal which is shown in the first floor. And we have calculated the noise rate. For that, we have collected this signal from the SIPM where the LED is off. And noise rate is estimated by the fraction of events crossing the charge threshold out of the total events. The noise rate as a function of charge threshold is shown in the second. So in this experiment, we have performed the VI characteristic of the SIPM and photoelectron spectrum of the SIPM as a function of load voltage, and breakdown voltage was estimated from the gain versus bias voltage plot, and noise rate of the SIPM was estimated. So we would like to thank the organizers of the ICFA school and lecturers and instructors and also all the staff members of the TIFR.
Thank you.
Thank you so much.
So slide tips. Yeah, did you measure the current? You measured this current.
Yes.
Yeah, and why is that the dark and LED on has the same current?
So actually, so we have the high frequency. So the noise frequency is very high. It's all in the order of 10 to the power 5. But this LED's frequency is just 400 hertz. So when for this frequency rate, so this dominates, the current dominates in the device.
So basically what we are saying is that LED light was very, very low.
Then this frequency is very low.
Noise is much more.
Noise is much more. Right?
Yeah. Did you operate the your silicon PM at different temperature?
No. So for this For experiment, we just did on the room temperature.
What will you do?
That's separate experiment.
So, slide 7, slide. Yeah, so here, I can say graphs, I see two effects. One is increasing the height of the pulses, and the other one is the separation.
Yes.
So what is the reason for the two?
So we have increasing the biasing voltage. So we are collecting more and more. So the avalanche is more and more. So we are getting the more and more charges.
But what about the spacing?
Space
Space again also increases. The field increases, the gain increases.
the collection of total charge.
What really limits the target? Noise. What really limits the noise? The dark current. How the dark current is affected?
I didn't get so.
This measurement, how the dark current affect in this measurement?
No. What really changes the dark current?
Okay, so we have the where thermally generated carriers will be there. So they are producing the dark currents with thermal electrons which are produced, and also there are mostly the thermal electrons when we are applying the voltage, they can also make the avalanche, and they can also give some signals, but with very less intensity charge.
Can it take a phenomena which can change this? I mean, the sources which makes the dark current.
I didn't get so. Sorry.
What is the sources of the dark current or any other environment where you can reduce the dark current?
The temperature is one of the factors, so we can reduce the temperature. Okay.
Okay, thank you.
So, hi everyone, my name is Ashish, and we with Kunal and Chandra Prakash are going to present this activity for measurement of ion lifetime using a central detector. So my part is the introduction part, and for introducing muons, muons are basically second generation electrons in the standard model of particle physics, and these were discovered in cosmic rays by Carl Anderson and S.H. Niedermeyer in 1937. This is generated when cosmic rays collide with the particles in the upper atmosphere, and then produces the cascade of these interactions and so this produces pions, and pions further decays into the muons, and from there we get these muons we are interested in. These are useful in the study of cosmic physics, and it is also a background for most of the experiments related to the neutron oscillations experiments and the neutron astronomy experiments. Also, finding the lifetime of the muons will help us. Is directly related to the Fermi coupling constant we have. Okay, so little bit basics of muon decay. This is basically kind of this is an electron. So the interactions are similar to the electron, and the mass of the muon is around 200 times of it. This is the PDG figures given, and the mean lifetime of a muon is around 2.2 microseconds. Here is the Feynman diagram for the muon decay, which is
which is mediated by the W minus boson. So yeah, the probability of decay in time interval from T to T plus dt is given by this expression, and this will be used for finding the lifetime of the muons. Okay, so our objective is to measure the lifetime of muons, which requires first of all detecting the muon, then detecting the electron which is decaying from the muons, and then measuring the time difference between the signals from the two. So yeah.
So here we are only interested in muon that decay inside the plastic scintillator. Right. Okay. So we are measuring the lifetime measurement using plastic scintillator detector. So this is our experimental setup. For this setup, we have plastic scintillator, and for this photomultiplier tube, and HV supply for this photomultiplier tube, and data acquisition system. So for this, so working principle of this plastic scintillator is that when the charged particle passing through the plastic material, when the molecule get excited by absorbing the energy from the charged particle, and de-excited by emitting through the light photon, and the light photon get interact with photo cathode and get electron. So the photo electron multiplied through the photo multiplier tube with diodes, and that we get the signal. So when the muon decay inside the scintillator, we will get two signals. Like this one is the muon signal, and this is for electron signal.
So as he said, we'll have a muon signal first, and then if it decays inside your detector, then we'll get another electron signal. We just connect these things to, the cables, instead of your computer, we just connect it to an oscilloscope, and we see a very nice muon peak. And if your eyes are good enough, you'll also see some of these electron peaks, which are the decayed electrons, well, signals from the decayed electrons. So what we do is that we have an 8-bit counter, we have a 10 megahertz clock. So in steps of 0.1, we can measure from intervals from 0 to 25.5 microseconds. So we just measure the time difference between these two signals, and between muons and electrons, multiple of those, and then we just plot it. And as we expect that the decay is supposed to be exponential, so we fit the data, and of course we get an exponential fit. From that, we can get all the parameters of the fit, which gives us the lifetime as 2.2 microseconds with some error, which is in good agreement with what you would expect from PTG, like what we have as the PTG values. So in conclusion, this was once we had muons and decayed electrons, and we had a very effective, very cost-effective, nice tabletop experiment, and we could detect it. So there's a nice phrase in Hindi, a very nice romantic story in Hindi, which is called "Ek tha raja, ek thi rani, dono mar gaye khatam khan," which is like, there was a king, and then there was a queen, and then we measured, they met, and then that's the end of the story. So that's how we felt while doing the experiment. We had a muon, measured it, electron, measured the difference, and we could do it. And everyone was talking about what their experiments are, or the detectors are used nowadays. So this, at the moment, I wouldn't say it's very fun, but traditionally it's a very cool experiment, because it tells you can actually see that the time relation, which sort of proves spatial relativity, and you can measure muons and electrons. So technically it's quite cool, I would say. So thanks.
Suppose you had a different kind of acquisition system, going up to smaller times.
Yeah.
Would you expect to see the same kind of lifetime curve that you saw?
Yeah, because a part of an exponential is still an exponential, so we would still get an exponential, just a bigger one.
No, what I mean to say is, there are two charged species of muon.
Yeah.
When they stop in this plastic scintillator, do
They have
they have the same life?
No, they have slightly different lifetimes.
Slightly different. How different?
I think one is 2.1. Yeah, one was like 0.1 microsecond or something.
Like that.
So because they interact differently with the nucleus in your detector, so like the electromagnetic interactions would be different. I would think
Magnetic, no.
because I mean,
Think about it.
yeah. I was
You are measuring the distance, the time difference between the two pulsars.
Yeah.
Okay. If the second pulse, instead of coming from the decayed muon, it can come from the another muon or another particle.
It can.
Yeah.
Yeah.
So how do you achieve it?
So that's why we have a time measuring circuit here. So we start a trigger when we get a muon, and then we expect a decay, like a delayed signal. It would be our electron. So if another muon comes at the same time, we want. So that like those kinds of measurements are just thrown.
Another thing is what constraint you have on the scintillation detector, because not all the muons which is passing through. It may not.
We have, if you're saying like if we have a voltage threshold, it's 42 millivolts or something like that.
No, for the detector, on the size of the detector, or you can do the same experiment with just 1 millimeter or 1 centimeter scintillator detector.
Well, you can, but you'll have to wait longer.
It has to decay, so you require a larger volume.
Oh, the volume, yeah, but yeah, I thought you meant the cross section. But okay, yeah.
One simple question, slide 10. The plot. Yeah, so you see many different kinds plotted here, right?
Many different what? Yeah.
Some events at different times. So how is this related to the lifetime? And you showed a bit and the formula and the, but I mean, why are you getting events at all these different times?
Because I mean, it's not so. The lifetime is like, you have a probability. So it's mainly like it's supposed to decay around 2.2, but it can of course go longer or decay before that.
Okay, I just have one more question. So what about the lifetime of the electron?
Well, electron is stable.
Okay, thank you. Thanks.
So hello everyone, we're Seven, and we're going to tell you about this microcontroller. I'm Gani and I will start. Silicon photomultipliers have found their own use in a scientific experiment. It's a solid state photodetector with high amplification factor and is capable of single photon detection for various scientific experiments. Well, many applications require stable gain of photodetector with respect to temperature changes, because temperature changes can bring on gain changes. So in order to keep gain constant, we put our photodetector in a constant control temperature, or we put it in a normal environment, but we also it also employs this gain compensation circuitry. So there are few approaches for temperature control in SIPMS include. We can set temperature sensor located very near to SIPM sensor to adjust power supply voltage. And we can also use average SIPM current as a temperature sensing signal to adjust bias supply voltage.
Well, here you can see SIPM structure. SIPM is an array of microcells. It's an array of microcells. Here you can see the top view of it, and here you can see the side view of it. And also here is electrical equivalent circuit of microcell. Here is this aromatics, here is the oxide, and here is the resistor. Going forward, here are some equations we use for our experiment. You can see here that we calculate the gain of SIPM, having this average chart and divided it into charts. And the broken voltage, breakdown voltage, sorry, which is the minimum bias voltage that leads to some suspended average multiplication in SIPM, sorry. And here is the over voltage, which is divided in terms of it's a bias voltage minus breakdown voltage, and here is the final formula of the gain of SIPM. Well, here you can see also the biasing process of SIPM. Biasing is the process of assigning a voltage to the SIPM to control its performance. And here you can see also the diagram of thermoconstructive SIPM. This is the final thought of my talk. And here you can see the temperature dependence from breakdown voltage, and the temperature coefficient of SIPM refers how its performance changes as the temperature changes. And finally, the SIPMs typically have a negative temperature, which means our gain is decreasing when our temperature is decreasing. So next one,
I'm going to talk about the experimental setup of the silicon photomultiplier. So the motivation is to talk about this silicon photomultiplier is that it has high amplification factor, and we are using it in the rich detector at LHCb, and it has various applications like PET and cytometry, and in other fields like particle physics, high energy physics, and nuclear physics. We can use it in security models, like we can monitor the radiation, and it operates on the very low voltage. And the best thing about this silicon photomultiplier is that it is not immune to the magnetic field, and it has the capability to detect the low light levels. And the only problem with this silicon photomultiplier is that it is calculating the variation of the gain as a function of the temperature. So if the temperature is variating, the gain will be lesser and lesser. So here you can see the silicon photomultiplier, which we are using with the 16 channel 4x4 and the 50x50 micrometer pixels, and it has some dead pixels. And here, which is the board we are using for the temperature as a temperature sensor. We install one chip here on the 8th number channel, and we have two sensors here. These are temperature sensors, and here is the serial number of this sensor, which is developed by Hamamatsu. And here we are using the function generator. So here what we are doing is we are giving the TTL pulse, and then we are using the level translator. What it does is that it is getting 3.5 volts, and we are converting it into the 800 nanovolts. We are using the discriminator to ADC converter, and we are getting some signal to the oscilloscope. Sorry, I didn't connect this. We are getting some signals from here, and then we are using the light nano source. So we are connecting that light source with OFC cable with the environment chamber, and we are giving some bias controller to this environment chamber system, and we are controlling our bias using the Raspberry Pi controller. So it has been calibrated by the team here with the high energy physics group. And so we are getting some signal here from the environmental chamber. We are getting some signal on the oscilloscope, and we read our we get the data from here. Then this is the environmental chamber here. It is connected with this PC, and here is all the instrumentation. So the main thing here is that this is our setup. Here we on the corner, we have the SIPM board. We connect it with the photomulti preamplifier, and then at the end we have the temperature compensate board. So this SIPM board is it can operate on the -60 to 125 degrees Celsius. Also, this environmental chamber can burn from -50 to 125 degrees Celsius. It has the capability to change the temperature per minute 3.5 degrees Celsius, and then we control our this chamber using this Raspberry Pi. And then so the team from the high energy physics group, they have developed this application. What we are using is here is that we are controlling our bias card using the menu here, and then we are using the terminal to interact with this software. And we are just changing the temperature compensation off and on, and then we are monitoring our start, and that's just we get the readings. We just change the temperature here -10 to 30. We can change it a little bit more if we want more data. And also in the previous slide I have shown we are just using one silicon photomultiplier. We can use multiple photomultipliers to get the data, and here using the terminal we get the data. Now Prabhat will discuss about the results.
So what are the experimental observations? So we change the temperature of the environmental chamber from 30 degree to -10 degree. We see the SIPM sensor temperature, corresponding temperature, and the pulse amplitude of the signal. And we see that the bias voltage is constant when we do not do the temperature compensation is off. So bias voltage remains almost constant, but over voltage increases. But when we turn on the temperature compensation circuit, so we see that the bias voltage reduces and the over voltage is constant. So we want that the over voltage should be constant to get the constant gain. So here I plotted the SIPM temperature versus the over voltage. So when the temperature compensation is off, so the blue curve shows that the over voltage decreases. But the temperature, when the temperature compensation is on, so the over voltage is constant. So this is what we require. And this is the plot of the SIPM temperature versus the pulse amplitude. We see that when temperature compensation circuit is on, the pulse amplitude is almost constant, but when it is off, it decreases. So it means that the gain of the SIPM changes when the temperature compensation is off, but it remains constant when it is on. So conclusion is that for a fixed bias voltage, the gain of SIPM changes linearly with temperature because the breakdown voltage varies linearly with temperature. So we have to adjust the bias voltage by the help of bias control and temperature compensation circuit, which so that over voltage remains constant, which eliminates gain temperature dependence. Thank you.
Would you recommend the noise rate as a function of temperature? Or a given over voltage? Might have been an interesting point. I understand.
Slide 30. Okay. Yeah. So what is this Raspberry Pi?
So Raspberry Pi is the module we are using at computer. So it has a microcontroller, and we have given it code so that what it does is that so we are getting our temperature. After validating the temperature, what is happening is that our bias voltage is changing, but we are keeping it constant using the ambient temperature of the room. So it's like two-way system. And we are also controlling that Raspberry Pi with power voltage with some setup.
This code that you gave, you input to the Raspberry Pi, do you write it yourself? Or
No, unfortunately, we just have 4 hours session, so we could not write it, but we can write it.
Okay, thank you. Thanks.
Thank you.
use materials. Yeah.
Hello. So today we talk about chemical detectors and about edge detectors in particular. So let's talk about first about the Cherenkov effect. It's named after Russian scientist Cherenkov, and when particle moves, a charged particle moves through the medium with a speed that is greater than the speed of light in that medium, it produces the radiation. The radiation is moving in the form of foam, as you can see. As you can see in this picture, and cosine, and it moves in the form of foam, and the cosine angle of that foam could be given by that formula. And in order to achieve that radiation, the particle must move with a speed greater than the speed of light in the medium. So how do we use Cherenkov radiation to detect particles? One of the ways is to use so-called ridge detectors. What is a ridge detector? A ridge detector is, first of all, the thin layer of medium that particle passes and generates a Cherenkov radiation with the form of foam with a small width that is corresponding to the width of the layer of medium, and transits to the plane where photomultipliers collected signal. As you can see, it forms a ring. This is why the detector called ring imaging Cherenkov. And by measuring the radii of the rings, we can determine the angle of the Cherenkov radiation, and then determine the velocity of the particle and distinguish different kinds of particles. So our goal for this work will determine the properties of the photomultipliers that we use in our work, then see the diffraction pattern caused by individual photons that are passing through the slit, and the third one is to see the Cherenkov rings that were generated by the photon passing through the ion channel. So in our experimental setup, we are using Kawamatsu multi-channel photomultipliers, L16, M16, and so on. They are position sensitive, and because they have multiple anodes at different positions. And we also use 2 layers of aerogel with multiple layers of medium. When constructing the ridge detector, we can create somewhat of a focusing effect, where the width of the ring that is generated can be decreased. And so we're using 2 layers of aerogel that are kept in the box, and here we have photomultipliers. So in the first experiment, we measured the properties of the M16 photomultipliers, their voltage plateau, and their spatial sensitivity. For that, we use this setup that is shown on the picture. We have LED light that is passing through the collimator into the box, or into the photomultipliers that is powered by high voltage, and then it goes, and the signal from the photomultiplier goes into amplifier, discriminator, and into the mean scale. And this is a picture of the setup. Here's the LED the collimator and the photomultiplier. And this is the result of the first experiment. First, we measured the noise counts that are passing in the detector over time. The reason for this, because when we first turn on the high voltage, there are some transition effects that cause it to have some additional noise, and in addition to that, there could be some additional light left in the box. So for that, we waited for some time and got the results, and as you can see, the noise levels are gradually decreased over time, so we can work with that multiplier thing. Next, we change the high voltage applied to the multiplier and gathered for 4 different multipliers. We gathered 4 different curves of the voltage, and as you can see, there's for all of the 4 multipliers, there is plateau voltage region, whereas the most stable have the best signal noise ratio and so on. Then we looked at the spatial distribution of the 4 multipliers. For that, we moved the LED source, and for all 4 different photomultipliers, we collected the signal. As you can see, there are some points where sensitivity is lower than average in the photomultiplier. So this is the spatial sensitivity of the signal.
So I will be explaining about the other two. The other two experimental setups. So the previous one that they did before, it was with the M16 photomultiplier. So it has basically 4x4 grids. But here we will be using the L16 photomultiplier tube, and it basically had 16 strips. Here you can see the 16 strips, and each are of 16 mm length and 1 mm pitch. So we will be seeing a diffraction pattern using this LED. So for the experiment, we actually used a laser, but here it's given LED in the schematics. So we had this setup, a laser, then a diffraction slit, and then our photomultiplier, and it's going to the photomultiplier grid, and then to the amplifier, discriminator, and finally we will be reading the outputs from the scaler. So this is the picture of the setup. So this setup was inside the box, and outside of the box we had all our connections. So here we had the laser, the slit, and after some distance we had our PLT and the output wires going out towards the scaler. So basically what we did is this photomultiplier we moved from this side to this side, and we observed the diffraction pattern. Okay. So here you can see the diffraction pattern clearly. We have our maxima, and then the first minimum, and so on. And it's not very clean because we actually didn't subtract the noise from this one, because there was a noise pattern. Okay. So for the next experiment, which was the most exciting one, so we had this setup with the aerogel radiator, which is our Cerenco radiator. So the setup we had a scintillator which will act as our trigger, and then we had the aerogel radiators, and finally we had this PMT structure. I will show in the next slide how the PMTs were arranged. So basically we had a similar kind of setup in bell to arrange detector, where it performs the PID, or the particle identification. So this is the setup. We had the scintillator, then the aerogel, and these are the PMTs. And if you see, it is like a 6x6 grid, and these are the M16 PMTs. So each has 4x4 kind of grid kind of structure. Okay. So I hope you can see the rings. So these are the cosmic muons, and this area that you see, these are the active areas of the multiplier, and the dark blue area, these are the gaps in between the photomultipliers. So we were able to see some of the rings from the cosmic muons. So coming to the conclusion, so we basically did the position sensitivity test for both the multipliers, and we observed the diffraction pattern and the Cherenkov rings as well. And so it kind of gave an idea of how we use Cherenkov radiation for particle identification.
Thank you.
Can you estimate the number of Cherenkov photons for that length of
Yeah.
aerogel?
So we should get on average around 14 to 15 Cherenkov photons. But here actually the acceptance of this photomultipliers, that was around 36%. So we can expect 4 to 5 photons.
Also, there is a quantum efficiency.
Yes, there was a quantum efficiency. I don't exactly remember them. Coming from. So we need the track information, and also if I remember in our detector we do the time of propagation, so we know from where the particle is coming from and where the ring is, so we can find the angle and we can identify the particle from that.
How do you identify the mass? You have the ring.
Yes, so by simulation we actually make a PDF of how the ring will look for what particle, and when in actual data taking, when we get a ring, so we match it. So we basically find the likelihood function. So from that, you can say that this is more likely to be K1 or phi.
No, what you get from the ring is only beta. And
Yeah. I mean, we need more information from the ring.
So provide to slide 6. Yeah, okay. That one we also. So next one. So why do we need the coordinator?
Because we want our beam to be focused towards the beam.
What happens if the beam is
like the photon can go in any direction, but we want it to be concentrated towards the beam.
It's also for the polar diffraction. To see that.
He's asking about the coordinator.
Okay, then. Thank you. Thank you. You can start.
Good afternoon, everyone. We are group 30, and today we are going to present the lab session on basic properties of silicon sensor. This is the overview of our presentation. And let us first start with the basic of silicon sensor. What really silicon sensors are? Silicon sensors are normal P plus I N plus type of diode, where P plus means the high concentration, P plus and N plus mean high concentration of doping, which is of the order of 10 to the power 15 atoms per centimeter cube, and I is very likely though P type or N type silicon, where the concentration is almost 10 to the power 12 atoms per centimeter cube. To act as a detector, we have to give reverse bias to the diode because we don't want any leakage current due to these thermal electrons. And we want the depletion region to be throughout the volume of the detector. So we generally give the operation voltage above the full depletion voltage. There are different types of silicon sensors. In our experimental setup, we have used silicon pad detector, which is a normal silicon junction diode, we can say, or strip detector. Therefore, strips are introduced so that we can also measure the position of the charged particle. When a charged particle enters the detector, it creates electron hole pairs, and these electron hole pairs, when they travel to the detector, then we get the signal. In the first experimental setup, we use transient current technique to study the properties of silicon pad detectors. Transient current technique is a tool which is used for studying the properties of silicon detectors over 2 decades. The basic properties of silicon sensor that is used in studying the property is the non-equilibrium free charge carriers. Since silicon has a very low band gap, so we can use light to create the charged particles, and the amount of charge that will be collected, or the signal will be given by the Shokiremo theorem, which says that the current that is induced is the dot product of the velocity of the particle and the weighted electric field. The weighted electric field is the electric field we calculate when we just apply 1 volt of potential to the collecting electrode, and all other electrodes are grounded. For a simple pad detector, the weighted electric field we get is 1/d, and since velocity is mobility into electric field, so we get this expression for the current, and to get the charge, we integrate over the entire range. These are the detector specification we have used. We have used a silicon pad detector, which has a thickness of 300 micrometer, an area of 5 millimeter into 5 millimeter, and resistivity of 16 kilo ohm per centimeter. This is the schematic view of the experimental setup. We have a laser source, and then we inside this we have our detector, and we have used a bias T circuit to provide signal to the amplifier, and also to provide high voltage, and this amplifier signal is then taken to the oscilloscope to see the results. This is the picture of the experimental setup we have used. Here is the laser pulse, and inside this we have our detector, and we have our high voltage here, and this is the high voltage filter circuit. And here we have shown DRS, but we have seen our results on an oscilloscope. This all from my side.
So we will be using laser light to create the electron hole pair. So we will put the laser light in such a direction so that we can separate the hole and electron in the signal. So we put the laser in one side of the PN diode, so that hole or electron get absorbed in one diode, and another type of charge carrier, that is electron, it's traverse through the gap, traverse through the medium. So the laser light we are using has penetration depth about 1 micrometer. So it will create here electron hole pair, and then the creating hole will induce in the P diode, and electron will travel towards the N side. So what happens that the moving electron will induce the signal in this electrode, and as she said that it follows the Softler-Amos theorem in the previous slide. So
Okay, so from this Shockley-Damon theorem, if we know the transient current, we can get the electric field profile, and we can measure the drift velocity, and also we can measure the drift time. So when the voltage is very less, when bias voltage is 0, we'll get some signal here, but this is the induced signal, but the signal is not going to the the electron charge is not collected here. So it takes infinite time mathematically to get to this end. And after we get to the voltage 10 volt and 30 volt, above 30 volt, the depletion region is full. So depletion region is in this thickness, and we get the charge collection here. So this is the charge collection time. In between this time, the electron in this diagram, electron travels through this gap. The intensity of the field is measured by the steepness of the slope, and the slope value gives the is it traveling from the high field region to low field region, or the low field region to high field region. So in this region we have applied high voltage air, and electron is going from low voltage region to high voltage region. So slope is slope is the negative slope. And here, as you can see, red light is illuminated on negative side, slope is positive. So that means hole is going from low field region to high field region. And then we have measured the drift velocity and mobility using oscilloscope. So from this region, the induced signal has started, and here induced signal is collected in the diode. So we have taken this time. This is the drift time, the electron drift time, and we measured from the voltage, and from the voltage we calculate the electric field, that is voltage divided by the distance, but that thickness, and we measure the velocity, drift velocity, measuring the drift time, and from this drift velocity we measure the mobility, that is the velocity under electric field. So what we have observed, that drift velocity saturates after some time, as you can see in this region, that after if we increase the bias voltage, reverse bias voltage, the width of this region is being constant after certain voltage. So we have measured the mobility, and mobility also got saturated. And we have so after this we will talk about the Alibaba experiment.
Yeah, I will start like hello, good afternoon, everyone. Hello, good afternoon, everyone. So I am going to describe the properties of silicon strip detector, and for that we use it Alibaba readout systems. This is the schematic diagram, and the below picture is the setup that we are working in the INO. And I will describe the component for the silicon strip detector we are using is they use Atlas 12 protocol, which has a dimensions of 1 into 1 centimeter, and its thickness is 1300 micrometer, and it has a 100 strip. The above one is the P-type and the below one is the P and type sensors. And and in Alibaba setup, there is a better chip, which is has good read of chip, which is a 128 channel each. And also use it regards the device with scintillator trigger plus the ND, which help us to store interesting one. And there is also a hardware called pile-up, which is used to store the event in better chip and wait for trigger response to keep an event or not. And there in readout system, there are two main components called dashboard and motherboard component, which is connected to USB through DC. And lastly, we use it CZM157 source to study the ionization energy. But as we know, to study the spectrum, we need to know the noise. So with our source, we measured the noise. There are the main two sources of noise. One is the gauge current, and the second one is due to detector capacitance. And we observe that as we increase this depletion voltage, the leakage current is become saturated as we increase it. Also, the right plot is as we see as we increase the voltage, the mass ADC is become less and saturated at certain point. Then we load the source and to extract the signal 1 minute, sir. To extract the signal, we cut off the pedestals. And we consider only those signals which has a SNR greater than 10. And this is the spectra we obtained when we released the. And we also calculated the gains and number of electron contributing noise. And this is the summary. Thank you very much.
So you don't know anything, but you finish in half a minute. Now, okay.
At what temperature did you maintain the detector?
We at room normal.
You did not cool the detector.
Yeah, we actually
you cool it.
Yes, there is also a. I will not.
No, what happens if you cool the detector? Let's say in liquid nitrogen temperature or something like that. What do you think will happen?
We got a better signal. Noise will drop.
Yeah. Okay. So that's LTR cooling system. Do you know how it works?
Actually, in failure cooling system, in one side we have, if we keep some temperature, it will, in another side, it will give another temperature difference. So if suppose if I give in one side.
But anyway, why was that cooling needed?
Cooling is needed for the thermal fluctuation of the detector.
Maybe the ionization charge it comes again and it may heat up the detector.
Okay, so using Peltier cooling, what was the temperature at which you were keeping the system?
We'll look into it.
Okay, anything more? Okay. Then thank you. Thanks to all of you. Only one word I can tell that when I was in that your age, my presentation would have been much worse, and this senior can tell about what was my presentation during that time. Now I request these members if they want to say something to the students.
And it is comparatively for your excellency.
I agree, I concur.
Yeah, all of you did a very good presentation. Your preparation of slides and your things are quite good. And some of them had a little problem about speaking or communication. With others are good in communication. But the experimental work, whatever you people have done, is quite good and you people have understood whatever you have done.
Both of my colleagues, the only thing, I would say that the questions that we asked, maybe not all of them were well focused and we ourselves also devoted much time. But still, whatever questions we asked, please go back and check the answer or try to understand a bit more about the experiments. You also did not have much time, so spend a little more time to get more of it. And I don't
Okay, then we'll break for lunch and we'll come back at 2 o'clock. But you did not give me the answer that your certificate you will take from there or some of the senior will give you here. Okay. Okay. That is a little bit information. So I have no time constraint. Okay. Then after let's see that I will just say that. So the first when you come back, we'll give the certificate to all of you, some of the senior members. Also, small prize also be there, I listed at Lovis. And then by that time, last time, this people will look on this view and some of you will get some prize. And then I have to give the vote of thanks to the who are behind this scenario to complete. And at the end, there will be silence.